Hello everybody, this is Dr. Christopher White, and in today's presentation we're going to be looking at Paleozoic Earth history with a focus on the early Paleozoics. That's the Cambrian, the Ordovician and the Silurian. So in this presentation we're going to take a general view of global tectonics during the early Paleozoic, and we're going to take a more focused view on North American tectonics during the early Paleozoic. Okay, let's get going. So by this point we've made it all the way through the Precambrian and we're now into the Phanerozoic. So if you remember, the Paleozoic is one of the three constituent eons of the Phanerozoic, the other two being the Mesozoic and the Cenozoic. So by the end of the Precambrian we've managed to form a substantial portion of most of the continents, with the exception of Europe and Asia. A lot of the build-up of those two continents occurred a little bit later. Also in the Precambrian we've had our first three supercontinents, so that's Nuna, Rodinia and Panatia. So the breakup of Panatia and a sudden rapid increase in plant and animal fossils marks the start of the Cambrian. So we can see these changes as we transition from the Precambrian into the Cambrian. We can see a sudden increase in the amount of passive continental margins. So that, if you remember, those are the nice, safe, boring marine environments in which life loves to live. And if we look in the rock record, we can suddenly see that the abundance of fossils increases massively as we go into the Cambrian, because the Cambrian is marked by the appearance of large numbers of macroscopic organisms, or organisms that you can just see with the naked eye. And a lot of those organisms will have hard shells or skeletons, in which case they are far more likely to fossilize successfully. So we'll see these animals appearing in the rock record in the form of fossils a lot more commonly than the more soft-bodied organisms we had right at the end of the Precambrian. So during the early Paleozoic we have sediments being deposited on cratons, producing two distinct types of environment. We have the platforms, so that's areas of Precambrian crust which get covered by younger sediments, and we have areas which we refer to as shields. Those are areas of Precambrian crust that are exposed, so you can actually go and physically touch the rocks, you can walk on it. So the rocks deposited onto the cratons during the Paleozoic consist of a mixture of detrital, so that's clastic, and chemical sedimentary deposits, which have been deposited into shallow seas underlain by continental crust. So the term for one of these shallow bodies of seawater which is on top of continental crust is called an Epeiric sea. Of course they're different to larger ocean basins where of course the water is sitting on top of oceanic crust. So during the Paleozoic and the Mesozoic, these seas transgressed and regressed due to periods of continental glaciation and or plate tectonic movement. So we're going to see large-scale global transgressions and regressions associated with either glaciations or, in one or two instances, actual large-scale tectonic processes. So sediments within these seas were deposited as horizontal layers. As most layers of sediments are, so they formed these nice sheets, so they were laterally extensive but quite thin. However, tectonic pressure could lead to the formation of gentle regional folds, which are essentially produce things which we refer to as arches, domes and basins. So obviously an arch essentially is just like a large fold. A dome obviously would be a three-dimensional fold, and a basin would obviously be a three-dimensional depression. So in many cases the topographic highs which are created due to the very gentle folding of these rocks which are being deposited into these Epeiric seas will form island chains, and of course these island chains will get pushed above sea level where they can be eroded, and they'll obviously provide a source of sediment which is then deposited into the surrounding Epeiric sea. So in terms of modern Epeiric seas, there are several examples. In terms of North America, the most obvious example is the Hudson Bay. In terms of Europe, there's the North Sea and the Baltic Sea. In Southeast Asia, we have the Gulf of Thailand and the Java Sea are good examples as well. And you can see that all these bodies of water are sitting on top of these areas which are marked out in this kind of light minty blue colour. And this represents essentially continental crust that has seawater on top of it. Compare that to the much deeper ocean basins which are marked here in the dark blue, and in that instance the seawater is obviously sitting on top of oceanic crust. So the next thing we need to think about are mobile belts. So mobile belts form during continental convergence, so convergent plate tectonics. And they're going to be produced by the deformation of continental crust and marine sediments during convergent plate tectonics. There's also going to be a certain amount of intrusive action going on as well. That tends to be more associated with convergent plate tectonics involving subduction. So for mobile belts formed on Laurentia's margins during the Paleozoic. So we have the Cordilleran belt, which is located along the west coast. We have the Epeiric belt, which is located down here in the south. We have the Franklin, which is located up here in the north. And we have the Appalachians, which are located here on the east. So the areas that are marked out here in brown pretty much cover the extent of the Precambrian crust as we transition from the Precambrian into the Cambrian. So this area that's marked out here in dark brown, that's the Canadian Shield. So for most of the Paleozoic, this area is going to be above sea level, so it can be eroded and it can produce sediment. This lighter brown area here, well, that's the platform. So that's the part of the Precambrian crust which will sporadically be covered by these Epeiric seas, and so younger sediments will be deposited over the top. So essentially that will bury the older Precambrian rocks further down the sequence. So let's think about Paleozoic paleogeography. So as we've discussed in previous lectures, if you work out the depositional environments for sedimentary rocks of the same age from numerous locations, you can produce paleogeographic maps for regions, continents, or even, given enough information, the entire world. So this can tell you what the environment looked like for a given area of the Earth's surface at a given time. Now, one of the challenges which we need to try and get over is to be able to work out where the continents were located during the Paleozoic. Now, this is relatively easy if we look at more modern rock. So if we think about the continents' current positions, we can work out where they were located relatively easily using two different techniques. The first technique we can do is we can look at the seafloor. So we can see that the seafloor has been spreading. We can take samples of seafloor rocks and we can date them to get a numerical age. And so what we can do essentially is, once we know essentially how the seafloor has been spreading and at what rate it's been spreading, we can then essentially just run the clock backwards and start subtracting out the seafloor. And what we'll see is we'll see the continents steadily moving to new positions as the seafloor is removed. And so we can use this technique to essentially allow us to move the continents back to the positions they were in pretty much when the continent of Pangaea was falling to pieces. Now, another technique we have is paleomagnetism, and this uses the magnetic signatures of rocks which contain iron-bearing minerals, particularly the mineral magnetite, to help us work out where they were located on the surface of the Earth at a given time. So we have these two different techniques which work quite well on more recent rocks, essentially everything that's about Triassic or younger. Now, in terms of trying to work out where the Paleozoic continents were, it's a little bit more complicated. The first problem is that the Paleozoic seafloor has been subducted and destroyed. It's gone. So obviously if we don't have it, we can't use it to try and work out, at what rate new seafloor was being formed, in what direction new seafloor was being formed, so we can't move the continents backwards using that technique. The other issue is that a lot of the rocks from the Paleozoic that have paleomagnetic signatures, well, they've been around for a while, in some cases, in excess of 500 million years. That unfortunately means there's been a lot of time for these magnetic signatures to be reset. And obviously once they've been reset, well, any data we get from that rock will not represent the original data. So the question then becomes well, how do we gauge where the continents were located during the Paleozoic? Well, the first thing we can do is we can look at structural relationships. So we've already touched on this one in the past. So when we look at the rock record, we can see, when rocks have been deformed, in what direction that deformation took place, and how intense or weak that deformation was. And so what we can do is we can look for areas of the Earth where we have deformation occurring at the same time, in the same orientation, and at the same intensity. Because most structural changes in rocks will be related to convergent plate tectonics or divergent plate tectonics. And so if we look at the rock record, we can look at the structures and we can look at the deformation that we have in the rocks, and we can start to say, right, well, these two pieces of rock during this time period were clearly moving towards each other, and then they ran into each other and they went and formed a mountain range. We can also say at this particular point, this big piece of rock started rifting apart and started moving as two separate pieces away from each other. So by using the structural relationships, we can gauge where the continents were relative to each other based on how they're interacting. We can also look at the rocks themselves. So a lot of rocks are actually climate sensitive to some degree. So we've discussed how each sedimentary depositional environment will produce a distinct rock type, or at least it will have some features which will allow you to distinguish it. And of course, these features are going to be a direct reflection of the environment. And of course, the environment is going to be a direct reflection of essentially the conditions of the area. Was it hot? Was it dry? Was it cold? Was it wet? Etc. So there are certain types of rocks we can look for. So we can look for desert-related rocks like red beds. They're obviously going to tell us the environment will be hot and dry. We can look for types of rocks like evaporites. That would also tell us that we're dealing with quite a hot, dry environment. We can look for rocks like coal. Coal tends to form in very hot, humid environments. And we can look for rocks like carbonates. And carbonates are a great rock for trying to gauge where you are on the surface of the Earth, because they have a relatively limited set of conditions in which they like to form. And we'll actually cover that in a few slides' time. So by looking at the rocks, although it can't give us an exact location, we can look at the rocks and we can say to ourselves, right, well, we know that based on the rock record, the continents were probably located maybe towards a pole, maybe they were in a temperate region, maybe they were in a more desert-like region, or maybe they were in an equatorial region. And this is, essentially this will be shown in the rock record by the types of rocks which are being formed. So we can use that to infer an approximate position. And of course, we can also use the fossils, because now we have plant and animal fossils in large numbers. And of course, once we know the types of environments in which these animals like to live, we can use them to make predictions of the environments in which sediments were being deposited. And that will also help us to gauge what area of the Earth we were probably in at that time. So during the Paleozoic, we know there were 6 major continents. So there was Baltica, which consists of Western Russia and Northern Europe, so Scandinavia. There's China, which consists of a large part of China and some of mainland Southeast Asia. There's Gondwana, that consists of Africa, Antarctica, Australia, India, Madagascar, parts of the Middle East, Southern Europe, and Florida. There's Kazakhstania, which consists of portions of Central Asia. There's Laurentia, which consists of North America, Greenland, Ireland, and Scotland. And there's Siberia, which consists of parts of Russia, east of the Urals, bits of northern Kazakhstan, and Mongolia. And so these are the larger pieces of continental crust that are moving around on the surface of the Earth during the Paleozoic. Now there's also going to be smaller pieces of continental crust moving around, and these are referred to as microcontinents. And most of these microcontinents will typically get destroyed during the Paleozoic as they run in to the larger pieces of continental crust and they accrete onto the side. Now, most of the time we're just going to ignore the microcontinents, but there is one microcontinent that's important to us, and this microcontinent is called Avalonia. And Avalonia consists of Western Europe, Newfoundland, and New England. And it's going to be important when we're thinking about the tectonic evolution of the eastern coast of North America. Okay, so what's going on during the Cambrian? Well, during the Cambrian, the continents are located at low tropical latitudes, so most of them are near the poles, and on the whole the continents were ice-free, and the oceans were circulating freely, which meant that seawater could circulate around the globe relatively easily. So there are nice big gaps in between the continents, and so the seawater can circulate through these gaps with relatively little effort. So we can see, if we look at the map here, so here's Laurentia, so what we would now call North America. Now, what you have to bear in mind at the moment, northern Canada is actually right here. The eastern coast of North America is here. Western coast is over here, and the Gulf region is down here. So at the moment, North America, or Laurentia as it is at the time, was actually approximately 90 degrees from its current position. Down here we have this microcontinent of Avalonia, which is right there. So we have Baltica, that's Western Russia and Scandinavia. We have Siberia, we have Kazakhstania, we have China, and of course we have Gondwana. So these are our major land masses, and you'll see the area is pretty much ice free. We have lots of shallow seas over here along the coasts of Gondwana and China, and we have some shallow seas along the margins of Laurentia as well. Now, in terms of Laurentia, it's separated from Baltica and Avalonia by this body of water here, which is called the Iapetus Ocean. And the Iapetus Ocean is going to be very, very important in the near future. So, in the early Ordovician, what's going on? So, by the early Ordovician, we have Baltica and Siberia are moving westwards. So, if you remember, Baltica's down here, Siberia's over here, and we're going to see both of them moving approximately westward toward Laurentia. Don't forget, in between them we have the Iapetus Ocean. We are also going to see that Avalonia will begin to drift approximately east, maybe northeastwards, and it's also going to begin to rotate. So if you look at the position of Avalonia now, you'll notice it's striking approximately northeast southwest, which when you compare it to the Cambrian, where it's striking approximately east-west. So you see it's essentially been coming round, and it's rotated slightly to a new orientation. Gondwana, which was over here, so if you remember, Gondwana is South America, Africa, India, Australia, Antarctica and Madagascar. Well, that was up here and it's steadily drifting southwards now, so it's going to start going over the South Pole. And we know it's going over the South Pole because we begin to see in the upper Ordovician the appearance of tillites. And if you remember, tillites are the rock which is formed by the liquefaction of tills, and a till is a type of sediment which is only formed by glaciation. So we know we must have large-scale glaciation going on Gondwana during the upper Ordovician, and so that would suggest very strongly that it's moving over one of the poles, and the data we have suggests it was moving over the South Pole. So by the late Ordovician, Avalonia has gone and collided with Baltica, so they've essentially formed one landmass, and the Iapetus Ocean in between Baltica and Laurentia is being subducted and destroyed. And so we're going to see this closure in the Iapetus Ocean in the formation of two mountain ranges. The first one is called the Caledonian Mountains, or the Caledonian orogeny, and the second event we're going to have is the Tectonic orogeny. And the Tectonic orogeny is going to affect the east coast of the United States in particular. The Caledonian orogeny is mostly focused in the rocks of east and northeastern Canada, Greenland and northern Europe. So by the Silurian, what's happened? Well, as you can see, Baltica and Laurentia have made contact now, and you can see that the contact is starting up here. So if you remember, this is going to be northern Canada. Once again, northern Canada here, western North America here, Gulf Coast region down here, and east coast of North America over here. So by the Silurian, we've got Baltica making contact with Laurentia, and of course that's going to lead to an orogeny, a mountain building event, and that's going to give us the Caledonian Mountains up here. Slowly over time, what's going to happen is what's left of the Iapetus Ocean is going to close up a bit like a zipper. So the rocks are going to start closing up, and we're slowly going to lose the Iapetus Ocean. It's going to get destroyed in an approximately southwesterly direction. So the last bits of rock to touch each other will be southern Avalonia hitting the east coast, or what is now the modern day east coast. Okay, and this collision between Avalonia and the east coast of North America, or should I say at the time Laurentia, would be the formation of the tectonic orogeny, and also the Acadian orogeny, which occurs a little bit later. So let's think about the early Paleozoic for Laurentia. So the Phanerozoic sedimentary record for North America contains 6 cratonic sequences. So a cratonic sequence is what's called a large lithostratigraphic unit. So it's a big stack of rocks. And this big stack of rocks has essentially, well, represent, should I say, a major transgressive regressive cycle. So they represent a big, thick sequence of rocks produced as the oceans transgress onto the land and then as the oceans retreat. And you can pick out these cratonic sequences in the rock record because the top and the bottom of them are marked by very large unconformities, which are normally craton wide. So they would normally stretch all the way from the east coast of modern day North America all the way over to the west coast. So the transgressive portions of these large lithostratigraphic units are often pretty well preserved, because obviously as new layers of sediment are being deposited, they naturally protect the layers of sediment below. And so during the first half, the transgressive portion of one of these events, obviously you're going to have lots of sediment being deposited, and so you're going to build up a nice thick stack of rocks. Now, during the regressive period, obviously, you're still going to have sediments being deposited and therefore rocks forming, but eventually, of course, the sea is going to retreat fully, and that's going to leave the rocks exposed, and they will therefore undergo erosion. So it's not uncommon for portions of the regressive part of the cratonic sequence to be lost, because, as I said, they were above sea level, they were open to erosion, and so rocks were destroyed. So where rocks of a similar age are preserved, the unconformities that mark the upper and lower boundaries of these cratonic sequences are observed to extend across all of, or at least over, large areas of North America. And when I'm talking about these 6 cratonic sequences, I am just talking about North America and the United States in particular. So this diagram here summarizes the events which are going on during the Phanerozoic. So to begin with, you can see this symbol here stands for the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, and then we have the Cenozoic. So these blue triangles are representing the orogenic events which are going to occur during this time period. The ones on the left represent events which occur on the modern day west coast, and the events on the right represent events which are occurring on the modern day east coast. And so what you can see is the width of the triangle here represents essentially the length of time. Obviously the broader the triangle, the more time the event took to occur. Typically also the height of the triangle here also represents the intensity of the event. So typically the bigger the event, the bigger the triangle will be. So if we look over here on the west coast, we're going to be discussing the antler orogeny as part of the Paleozoic. You'll notice though that's pretty much it for the Paleozoic on the west coast. Whilst over here on the east coast, we're going to be covering the tectonic orogeny, the Acadian orogeny, the Achetan orogeny, and the Alleghenian orogeny. Now, the middle portion of the diagram here is actually covering what's happening with regard to sedimentation on the essentially the continent of Laurentia / North America. So this side of the diagram here represents the modern day west coast. This side of the diagram here represents the modern day east coast. So these brown areas here represent periods of time where the continent was exposed, so it was above sea level. So if we come all the way down to the bottom of the diagram here and we look at the start of the Cambrian, what we can see is that a large portion of Laurentia was above sea level, so it was exposed and therefore it was undergoing erosion. What you'll notice though is that the amount of rock that's exposed gets smaller and smaller and smaller as we progress through the Cambrian. This means therefore that the sea must be transgressing onto the continent, mustn't it? So we can see we have the sea transgresses from the west, the sea transgresses from the east, and the amount of exposed continental crust is getting smaller and smaller and smaller. And so this is one of these transgressive regressive cycles, and this first one is called the Sauk, or the Sauk. Then we have another period where we have a regression, the continent gets exposed again, and then we have another transgression, the continent starts getting covered over, and this is going to result in the formation of the Tippecanoe sequence. Then we have a regression, period of erosion again, then we have another transgression that's going to form the Kaskaskia, another period of erosion, then we have another transgression that's going to lead to the formation of the Absaroka sequence, another period of erosion, then we have the Zuni sequence being deposited, another period of erosion, then we have the Tejas sequence being deposited, and then finally, as you can see, steadily the seas have retreated until we're back to our modern coastline. So this represents the modern east coast of North America, and this represents the modern west coast of North America. So once we have our 6 cratonic sequences, we're obviously going to subdivide them into smaller units just because it's going to make them a little bit easier to work with. So these smaller units are very helpful to us. Obviously they'll allow us to correlate rocks at different locations, and they also allow us to undertake high resolution analysis of time and facies relationships in sedimentary rocks. So what I mean by that is, because we've studied these 6 sequences so comprehensively, it actually allows us to track how the facies related to the sequences are moving over North America as the Epeiric seas are transgressing and regressing. So this led to the development of a part of geology called sequence stratigraphy. And sequence stratigraphy is the study of rock relationships in a time stratigraphic framework of related facies bounded by erosional and non-depositional surfaces. So what that really means is it's the analysis of these 6 sequences and how they move backwards and forwards over North America with time. So the basic unit of sequence stratigraphy is a sequence, of which North America has 6. And of course these sequences consist of a package of rocks which are obviously bounded by an unconformity at the top and the bottom of the sequence. So these unconformities obviously represent periods of decreased sea level, so low sea levels, during which time the continents were exposed, open to erosion, so rock could be destroyed and thereby produce the unconformities. Okay, so this is a good place to stop, so please stop the video here, get up, have a walk around, take a few minutes to relax, and then please come back for part 2.